Hello, this is Frat Tigrek. Today we will investigate another approach to testing if our hypothesis regarding the presence or absence of a signal is true. The t-statistic of the data at hand is used to assess the confidence in the validity of our hypothesis. Remember, Neyman-Pearson theorem compares the likelihood of two hypotheses based on the samples. The t-statistic is different. It considers the deviation from a single hypothesis, that is, the null hypothesis. We can say that the Neyman-Pearson approach focuses on making a decision and giving the probabilities that the decision is wrong. The t-statistics focuses on assessing the validity of the null hypothesis, measuring the strength of evidence against the null hypothesis. So, there is no intrinsic decision-making process. Let's start by considering the estimates of the expected value and variance of the distribution of our data. The estimates for the mean and variance are calculated according to the formulas given on this slide. For a data vector of size 10, the histograms of the estimates are generated from 30,000 repetitions of this experiment. As you can see, the estimates are themselves random variables. The peak of the histograms appear in the correct values, but what we see here tells us that there is a non-zero chance that our estimates deviate from the actual value appreciably. For example, estimating the expected value as larger than 0.5 is quite probable. So, assume we obtain indeed a 0.5 as the estimate of the expected value. Now, should we decide that our null hypothesis, which has an expected value of 0, is not valid and there's some other signal out there? Now, let's consider the same experiment, but data has higher variance. The visual inspection of the histogram for the estimate of the expected value tells us that the probability of obtaining an estimate that deviates from the actual value is even greater. If we obtain an 0.5 as the estimate of the expected value, can we say that the data deviates from our null hypothesis with the same confidence we had in the previous slide? The t-statistic gives an answer to our question. What it does basically is to calculate the deviation of the estimate of the mean value from the actual mean value and normalize it with the estimate of the standard deviation and the number of samples used in the estimation. The intuition is as follows. The t-statistic measures the significance of the deviation of the estimate from the actual mean. If the variance of the data is high, deviating from the actual mean is more probable, so the significance of the deviation is lower. If the number of samples increase, then the deviation is less probable, so the significance of the deviation is higher. Here is the crux of this idea. The t-statistic itself is a random variable with a very special distribution function, the student t-distribution. The t-distribution resembles the Gaussian distribution, and indeed it converges to Gaussian distribution as the degrees of freedom increase, but we are getting ahead of ourselves. What is this degrees of freedom that we are talking about? Well, it is the parameter nu in the probability density function of the t-distribution. Well, we don't need to manipulate this equation to get what we want. We have built-in functions in math programs and lookup tables to use the t-statistics and determine our confidence in the validity of our null hypothesis. Our goal here is to understand how the t-statistic works and how we can use it to determine the confidence in our null hypothesis. Before moving on, what is the degree of freedom really, besides being part of a complicated equation? The degree of freedom is n-1. Consider how we estimate the variance. We need to calculate the deviation of each sample from the estimated mean. For one sample, the estimate of the mean would be equal to the sample itself, so the variance cannot be estimated in this setting. You can say that there's no degree of freedom. If we had two samples, the variance is determined by the difference between the two samples. That means we have only one degree of freedom, which is the difference between the two samples. If we have a third sample, it adds a new difference term and increases the degree of freedom by 1. On the more practical side, let's observe the behavior of the t-distribution for different degrees of freedom. For lower degrees of freedom, which means lower number of samples, we have heavier tails. The t-statistic has a greater probability of deviating from 0. As the degrees of freedom increase, the tails become smaller and the t-statistic converges to Gaussian distribution. The interpretation: given the number of samples we use to make the assessment, if our null hypothesis holds, then the t-statistic will be below a certain value with a certain probability. The cumulative density function can help us visualize this statement. For a smaller number of samples, it is more probable for the t-statistic to deviate significantly from 0. Let's wrap up with a concrete example. The null hypothesis is the one described in the first slide. We want to develop a decision criterion to assess the validity of the null hypothesis. We want to make sure that when we decide the null hypothesis is not valid, we are wrong in only 5% of the cases. Deviations on both directions are possible. We have to choose a positive and a negative threshold for the t-statistic such that 95% of the null hypothesis cases have a t-statistic that is in between the threshold values. So, we choose the p-values, the probability of having a value below a certain threshold, as 0.025 and 0.975. The t-distribution is symmetric, so we just have to calculate the inverse cumulative distribution function of the t-distribution with 9 degrees of freedom for the p-value equal to 0.975. The threshold is found from the lookup table that is available in many references. This table is sometimes called one-tailed. If we were using a two-tailed table, we would just look up the value that corresponds to p is equal to 0.95. Here, we look up the t value corresponding to p is equal to 0.975 for nu is equal to 9. The resulting threshold, 2.2622, is the decision criterion we are looking for. As long as the t-statistic is between these thresholds, we decide that the null hypothesis is valid. The false alarm probability is set to 5%. In 5% of the null hypothesis cases, we will declare the null hypothesis is not valid. What about the detection probability? In this setting, the alternative hypothesis is not given. So we cannot talk about detecting something as we did in the binary hypothesis testing case. This slide concludes the investigation of the t-statistics. If you have any questions, please contact us. Have a nice day.